Hi, my name is Myungjung Kwon. I'm going to present our work, CATNet, Compression Artifact Tracing Network, for detection and localization of image splicing. First of all, what is image splicing? Image splicing is a type of image manipulation that copy-pastes some part of an image onto another image, as shown in the figures. This can be used for bad purposes such as fake news, false propaganda, or fake evidence, so it is important to detect image splicing. To be specific, our task can be summarized as: given a possibly spliced image, predict a mask that localizes the potentially tempered image portion. Then how can we do this? We need to distinguish between spliced areas and authentic areas. To this end, we mainly focus on compression artifacts. Most digital cameras compress images in JPEG format to save storage. Since JPEG compression is done in the DCT domain, compression artifacts are left in the DCT domain. By the compression artifacts, we mean the distribution of DCT coefficients. If we plot DCT coefficient histograms of the two regions separately, we can see the difference. In the authentic region, shown in green, a periodic parent appears, while the tempered region has no such parent. Okay, now we know the compression artifacts remain in the DCT domain. Then, why don't we use DCT coefficients as input to some good CNNs? This is a natural flaw of SAS, but unfortunately we can't. CNNs cannot directly learn from raw coefficients. It's because DCT coefficients are largely decorrelated and locally heterogeneous, unlike RGB pixels. So, this talk is mainly about how to make CNNs learn the distribution of DCT coefficients. This is our proposed network, named CATNet. It consists of two streams and a fusion stage. The RGB streams takes a normal RGB image as input and learns visual traces. The DCT streams takes DCT coefficients and a JPEG quantization table as input and learns compression artifacts. The fusion stage visits the two stream outputs. I'll explain three key points of the network. The first one is conversion to a binary volume. As I said, CNNs cannot directly learn from the raw DCT coefficients, so we convert them into a binary volume using this transformation and feed it into the CNN. Second, we use grid-aligned cropping followed by component separation. When training, images are cropped to a fixed size. The cropping box must be aligned with the 8x8 grid because JPEG encodes images into 8x8 blocks. This makes each channel of a channel-separated tensor represent a frequency component. The third one is how we pre-train the DCT stream. Each stream weights are initialized differently. The RGB stream is initialized with ImageNet, which is a quite common procedure. But the DCT stream is initialized by double JPEG detection. The DCT stream achieves total performance on double JPEG detection. This means this stream can learn the compression artifacts very well. For the main experiments, the network is trained end-to-end using spliced and authentic images. We used 6 public datasets and our custom dataset. More details are in the paper. The numerical results. CATNet achieved highest performance detecting image splicing compared to 2 SOTA CNNs. Here are some visual results. The first column is the input image, the second is our network, the rest is other networks. Green is correctly predicted spliced pixel, blue is correctly predicted authentic pixel, and so on. To see the effect of each stream, we conducted the same experiments using each stream only. Cover hole images have compression artifacts, and so the DCT stream performs well. In contrast, Columbia images are not compressed at all, so the DCT stream cannot work, but with the help of the RGB stream, the combined model performs well. We can say that the two streams complementarily cooperated to improve performance. This is the robustness test results. CATNet is robust to JPEG compression for various quality factors. Thank you for your attention.